geometric sequences in series. Now, geometric sequences is going to be a similar application of exponential functions because it behaves exponentially. Now, a good example of a geometric sequence is every year in March we have, well, except for this March, we have the NCAA tournament because in the first round we have 64 teams, and then the second round 32, then it goes to 16, the Elite Eight, the Final Four, and eventually the championship. So what you'll notice with those numbers is that it's getting cut in half every time. So there is some exponential applications happening here. Now, I had this exponential form in the previous video. Now, we're basically using that, and we're just going to change some of these letters, and it's going to look a little different, but it's still the same concept. So we're going to change the y to a sub n. The a is going to get a subscript, and we're calling that a sub 1. B, we're going to change that to r, and x, we're going to change that to an n minus 1. So what does all that stuff mean? Is that if you see an n, that's supposed to represent a whole number for that particular spot of that number in a sequence. So if a number is in the third spot of that sequence, the n is going to be a 3. If a number is in the fifth spot of a sequence, that number is going to be a 5. A sub 1 represents the first number of the sequence. So if I give you a list of numbers, the very first number that's there is your a sub 1. R is your common ratio, the pattern or the rate in that sense. Since exponential means constant multiplication, this is the number that we're constantly multiplying by. So here's an example. Write an equation for the nth term of the geometric sequence. Well, here's the geometric sequence. 0.5, 2, 8, 32, and so on. And we want to write an equation that's in the form of a sub n equal to a sub 1 times r to the n minus 1 power. And this is the pretty easy process. The first thing I need to do is, what's my first term of the sequence? 0.5 is my first term. So now I have a sub 1 is equal to 0.5. The next thing is, I'm trying to find my rate. So if I'm constantly multiplying by things, I can work backwards by using division to figure out what that rate is. Take 32 divided by the number next to it, which is 8, I get 4. You'll see that if I take 8 divided by 2, I get 4. And 2 divided by a half is also 4. So my r, my rate in this sense, is a 4. Now that I have a sub 1 and I have an r, where I have an a sub 1 and I have an r in the equation, I just simply substitute and replace those numbers. There's my equation. The equation for this particular geometric sequence is a sub n equals to 0.5 times 4 to the n minus 1 power. Now, what if I give you some information like this? It says a sub 4 is 5. That means that the fourth number in this list of numbers is 5. And I have a rate of 6 that I'm constantly multiplying by 6. So what you'll see here is I actually have 3 numbers that come before 5 that I don't know of yet. But using my rate, if I multiply by 6, I can get the next number after 5, which is 40. Now if I work backwards, instead of multiplying by 6, I can divide by 6. I get 5/6. Take that number divided by 6, which is 5/36. And one more time, I get 5 over 216. Now that number that's in the very first spot is my a sub 1. We already know what my rate is as an r, or r is equal to 6. So I take those two pieces of information and I plug it into my formula, and I get a sub n is equal to 5 over 216 times 6 to the n minus 1 power. Another thing that you'll be expected to do out of this particular section is find geometric means. Now, geometric mean is the terms between two non-consecutive numbers of a geometric sequence. So if I say find 3 geometric means between 2 and 1,250, that means there are 3 more numbers that are between the 2 numbers that I've given you. So I'm going to list those out with blanks because I have 3. I have 2, there's my 3 blank spaces for the geometric means, and then I have 1,250. One thing that you do know is I have 1, 2, 3, 4, 5 numbers in this particular sequence. So I have an n of 5, and my first term of the sequence is the 2. If I use that information going back to my geometric form equation, I can change my n's to the 5s that I have. I can plug in the a sub 1 that I have, and I can work backwards to figure out what my rate is. Now, if I got a sub 5 is the fifth number in that sequence, which is 1,250. I simplified my exponent, 5 minus 1, to give us 4. And I'm going to solve for r here. First, I need to divide by 2. Gives us 625 equals r to the fourth power. Now I need to get rid of that exponent by taking the fourth root to both sides. And when I take the fourth root, that'll cancel out the 4 for the exponent. And when I do the fourth root of 625, I have plus or minus 5. Now, why did I put the plus or minus the 5 in there? That anytime I take an even root to a number, I have to account for the negative number that also multiplied by itself even number of times to give us a positive. So there are two possibilities for my rate here. If my rate is a positive 5, I take 2 times 5, I get 10. 10 times 5 gives us 50. 50 times 5 is 250, and 250 times 5 is 1,250. But what would happen if my rate is a negative 5? 2 times negative 5 is negative 10. Negative 10 times negative 5 will give us a positive 50. Positive 50 times negative 5 gives us negative 250. And then the negative 250 times the negative 5 will give us 1,250. That's finding geometric means. Let's try another example. This time we're going to find 4 geometric means between the numbers 0.5 and 512. So I put 4 blank spaces between my two numbers. You'll see now that I have 1, 2, 3, 4, 5, 6 numbers that are actually in the sequence. So I know that my n value is a 6. And my a sub 1, my first number of the sequence, is the 0.5. I go back into my geometric equation. I can replace the n's with the 6 that I have. I can replace the a sub 1 with the 0.5. And I can solve from there. Now, a sub 6 on the left side, my 6th number of the sequence is the 512. I simplify my exponent. 6 minus 1, you get 5. And just like the last equation, I'm going to solve for r. I'm going to divide both sides by 0.5. 512 divided by 0.5 will give us 1,024. And just like the last problem where I took the root to both sides, this time I'm going to do the fifth root to get rid of the fifth exponent. Now the fifth root will get rid of the fifth power, but on the other side, the fifth root of 1,024 is just a 4. Notice that I did not put plus or minus in front of the number this time. I did not have to do that because my root is an odd power, or an odd index. So anytime that you have an odd index, you do not have to put plus or minus. So now we know the rate is constantly being multiplied by 4. I apply it. 0.5 times 4 is 2. 2 times 4 is 8. 8 times 4 is 32. 32 times 4 is 128. And 128 times 4 is 512. And there you have it. That is your geometric sequences with exponential functions.